Hello, welcome back to the Beating the Blackouts series. Today I'm going to build and solder, I should have some solder here, the circuit that we've been over so many times. Now I have up for reference my PCB design, and I might make the design available online, but you know, you guys probably do better if you really apply your minds. This is all done in a bit of a hurry. Excuse me. So the first thing to do when assembling a PCB in general, not always, is stick the resistors in. So we almost always stick the resistors in first. So I need a 10K, which is brown, black, orange. This is the 10K resistor. Oh, what is R3? Hang on one sec. That's interesting. Sorry, I must just get out the schematic as well. So I'll R3 is a 10K and R4, where's R4 on the schematic? I should show you guys this. R4 doesn't have a value because I wasn't paying attention. 1 second, I'll just get the value. So this is typically happens when you design a PCB. You often leave out one small thing, and then everything falls to pieces. R4 is a 22K. Okay. So R3 is a 10K, and just by matching up the holes, I can start placing these resistors in. So that's a brown, black, orange, which is 10K for R. Oh wait, let's just make sure. R3 is 10K. R3 is the 10K, and R4 is the 22K, which would be red, red, orange. There we go. So I put the resistor, I could probably do this neater if I pre-folded my resistors. Put the resistor pins fairly far apart, quite deliberately, because that allows for different sizes of resistor, different wattages. D2, which is next in this line, is a 1N4001. This one's quite important. If we get it the wrong way round, there will be trouble. However, I believe that's correct. Let me just consult my circuit diagram quickly. Yeah, that's correct. With the bar towards the base of the resistor. So that's 3 components in place. And if we move along, next in line is R8, which is another 10K. This is our R8. And then 3 resistors only. Yep. R8 is a 10k, then R5. What is R5, R2, and then R1? R5. I should have printed out a list, shouldn't I? But I didn't. R5 is also a 10k. And R5 happens to be oh, this is odd. R5 is the 10k, R8 is not the 10k. I'm probably gonna fast forward through all of this. R8 is, let's find out what our R8 is. R8 is unknown at this stage. That's for the on indication LED. We'll have to decide upon that shortly. We'll think about it a bit. So R5, R2, what is R2? R2 is 1.5k. 1.5k should be brown, green, red. So that's our R2. I'm just keeping these things up. And R1, our friendly R1, is also at this point unknown. This can't be right. No, where's R1 is 22k. Yeah, that makes sense. Which is red, red, orange. Yes. R1 is 22k. Red, red, orange. And then let's look for other resistors. There's another diode here. That's the Xena. Fits in here. I'm not going to do all the components today. I'm just going to do just enough to test base functionality. I think this might be all the known resistors at this point. Let's just check. R6 and R7. R6 appears to be a 1k. Brown, black, red. R6. And R7 is our discharge resistor. Which should be, I think it's a 1 meg. Yeah, it's 1 mega. So much neater without all the jumpers. So that's our R7. Trying to watch the open broadcaster and the board at the same time. Advantage of doing all the I'm just going to drop my soldering iron temperature. I don't know if you can see it so well here. I'm going to go down to about 320 and lock it. The advantage of doing all the resistors first is, of course, you can push the board flat. R7. Just check something. R7 does go to ground, yes. So this all looks fairly good, and we have reached temperature. So the secret in good soldering is you never apply solder to the tip of the, well, almost never. You can get a bit on just to help it flow. I think I need a bit more temperature here. 340 should do it. You don't ever want to apply too much solder to the tip of the iron. You rather apply the solder, and I maybe should have sanded this slightly. It might have corroded some in the interim. It seems to be taking solder better at this temperature. Anyway, you never apply solder directly to the tip. You normally apply it to the junction between what you're trying, the two things you're trying to solder. Of course, this may not be true for like plumbing solder, but oh yes, this is so the one disadvantage of this PCB is you need to be a little bit careful, just given the fact that the pads are quite small and it would be quite easy to make an unintentional short circuit here. I should actually move this up a bit so that it's a bit more visible while I do this. So the one thing they say in radio is dead air is a bad thing. So I'm going to make conversational small talk here. Did you see the game last night? Of course, that's an IT crowd reference. And well done if you got it. Gee. There's one disadvantage to these plated boards. They don't seem to take the solder quite as well as I expected. Still, it's much neater than the alternative. Yeah, I really think I should have sanded this down slightly first. Right, that's all the pins soldered. Some snips here. And I'll just quietly chop these off. So I'm gonna just go for it when I power this up. I'll set a current limit on the power supply, but I'm just gonna go right ahead and put full voltage on it and see if it works. This is not necessarily recommended. However, this is YouTube. So when you guys do this, if you're not very experienced, it's normally advisable to check for short circuits with a multimeter first, because who knows what could be going on. That looks like one, but I don't think it is. Lighting in here is a bit poor, sorry about that. I need to rig up, one of my next projects will be to rig up better lighting in this desk. Okay, so this is all the flat components that we know the values of. What we should do, just quickly, Let's get up a calculator. Window capture. New. Well, that doesn't work. Apparently I can't show you my calculations. Anyway, what it amounts to is I want to know to get 20 milliamps at a worst case value of 13.8 volts minus the, what is the voltage drop on one of these more rational LEDs. I want a more rational LED to indicate the, let's find, just hang on, I'm going to pause and find my LEDs and my tester. Be right back. Okay, I'm back. I found my LEDs and I found my tester. The reason I got the tester, I just want to know the voltage drop on one of these green LEDs. Notice how it flashes while it's testing. 2 volts. So we're looking at a maximum of 20 milliamps, although probably about 18 will do. 15 to 20 milliamps at a voltage of 13.8 minus 2 volts. So no. Okay, apparently I have to click what to work. 13.8 minus 2 is 11.8. Could have done that in my head. And we want a voltage of so we need a voltage drop of 11 volts, 11.8 volts, call it 12 volts, at a current of 0.02 milliamps, and that will give us a resistance of 11.8 divided by 0.0, say 15. That gives us about 800 ohms. And 800 ohms times, let's say 800 ohms, yes, 800 ohms times, let's just do this math in our head. It's no problem, I should really have a pencil and paper. But yeah, 800 ohms is a resistor I can dig up, or thereabouts. So bear with me while I go looking for a resistor. Okay, I'm back because I got a bit lazy, but basically the way I see it, we can actually just use this resistor. It should be about 900 ohms. Little bit more of a voltage drop. Yeah, that's it's supposed to be 910. Close enough. So 900 ohms should give us a nice bright LED that shouldn't be overdriven too much. Now, practically speaking, we don't want to just go ahead and wing this one because we're about to solder it. So my suggestion here, could stick it in, but we could just hold everything together. Connect that up. I'm at 13.8 volts. This should be our positive leg. That looks nice and bright. It doesn't seem to be drawing any excess current. If we are worried, though, we can do a current measurement. Let's go microamps. See what's the worst that could happen. Yes, the worst that could happen is everything could explode, but that seems quite unlikely to me point. The worst that could happen is I could misplace my meter leads. There we go. Actually, we probably do need milliamps for this one. There we go. I'm just going to connect that there and just get around here. 13 milliamps isn't bad. It's close enough. Let's just make sure it's still bright at the bottom end, actually. Let's drop this down to 10.5. So 10.5, the LED should still indicate, yeah, 9 milliamps. Close enough. They're rated at 20. Always put the meter back. So I suppose a 1K resistor here would be a bit more standard, but 13.8 is really workable. So the 13.8 is our R8. And our R8 is, where is our R8? Our R8 is this guy, which we didn't populate earlier. So let's just power on the soldering iron again and go ahead and solder this guy in. And that's the last of our flat components. Oh, this guy's not in properly. Let's wait for this to reach full temperature and force him in. He sits a bit flatter. That's a little bit better. Should really get a sponge for that. And that's our LED resistor. That's nice. One way you can check for, you won't be able to see it, check for shorts, is to hold the board up to the light. They generally let enough light through that you can see what's going on quite easily. Right. Next in line is our IC. And I have a little screwdriver to get this guy off the PCB. Not the PCB, the breadboard. And there we go. Now, pin 1, well, basically it should go like this. I said happily last time it would go in, but it doesn't go in so easily. Our pin 1 is our output. Pin 1 is our output. Let's just confirm that. Yes, pin 1 is our output. And pin 8 is our VCC. And pin 4 is ground. So it looks like the PCB is correct. So I'm going to go right ahead and solder the chip in. You're probably going to want to use a chip holder if you do this, but well, I've got 2 PCBs, so who cares? What's the worst that could happen? You know, the really absolute worst. Absolute worst is these things won't. There's no need to solder those pins, they're not connected to anything. This is not my best soldering work to date, but it'll have to do. Ah. Let's just make this a bit better. That's ground, it doesn't matter if it's a bit off. I really need to get better lighting here, and I may have to switch to a phone to record these things. Anyway, so we got the chip in. What remains is a transistor, which is this guy. And ground should be this pin here. Yep, that's right. So this guy is our transistor. Doesn't matter if he doesn't go in so well. We need our variable resistor. I think this looks about right. If not, it will trigger at exactly the wrong point, but that's fine. And we do need a MOSFET. I'm going to use a fresh one because I don't want to risk using a damaged one. Except where did I put my fresh MOSFETs? Oops. I might have to pause again. Well, no, they're here still in the packet I bought them. Here's a fresh MOSFET. I'm going to have to order some more of these. Seem to be going through them. Now the MOSFETs we also need to get right. So the MOSFETs, our MOSFET, if I'm not mistaken, is, yes, should be this way round. We may have to just confirm this somehow. Ooh, ow. Okay, I'm going to need another MOSFET. And I'm going to need to widen these holes. These holes are too small. Yeah, these holes are too small. So, that stalls this project slightly. I'll just solder the other things in quickly while I've got the iron up and running. The transistor can be soldered in. That's one thing to check, that your large components are capable of fitting into the holes. However, I don't foresee this as being too great a problem. Okay, right, I'm going to go drill out these holes a bit and I'll be back shortly. Okay, have fun. Right, I'm back, and by the power of YouTube, which apparently once you've made this many videos you can call upon, I have several days later drilled some slightly bigger holes into my PCB. Had to order a chuck for my Dremel because apparently it didn't come with one. So we're going to try a new yeah, that's much better. Goes straight in. I hope it will bond well with the solder after all that drilling. Okay, and we need an LED as well. Hang on one sec. I'm going to take a big green LED. Ooh, yes, this is where PCB design gets interesting. Maybe I can fold it forwards a bit. Because, yeah, that's what we need. then we can stick the LED in, sticking up as high as possible. That should do. Idea being that this will probably be mounted like this to a by some motherboard standoffs or something. I can always adjust the height of the LED later. So the LED will stick out through the case through a 3mm hole that I'll drill. Getting all the holes in the right place is going to be interesting, but maybe we can make some sort of a paper template, print something out. Anyway, so we've got the soldering iron at temperature now. Let's just make sure this is the right way round. 1 second. It's in what component was this? Can we read it? IRF Z44N. Z44N. And I should show you Googling this. So oh, this is awkward. Ha! I think I've made my PCB wrong. Just hang on, I'm gonna pause and check all of this. Right, the keen-eyed among you will have realized my mistake. Basically, the MOSFET that I designed this board for is not the MOSFET I had on hand, because they didn't have that in the KiCad library. And it turns out the drain and the gate are swapped. So, never fear, and I really wish I could zoom in here. My plan to fix this, you see, this is the gate, which should be here, and this is the drain, which should be there. But my plan to fix this is quite simple. We're going to cut this track here. I'm probably going to do it with a Dremel, and then I'm going to cut along here, and I'm going to keep the source in the on the ground here, and then we can bend this pin down to touch the gate, and bend this pin across and bridge this with some solder and maybe a bit of copper wire to essentially swap these pins. So not too hard, not the end of the world, but not something I can do at this time of night. Neighbors might complain. You guys know how it is. So I think that's about it for this video. I'm gonna start a new video, including some testing of the device later on. Okay, well, that was disappointing. Thanks everyone. See you next time.